So we now have Lou Kauffman on non-commutative calculus and non-commutative worlds. Pythagorean mysteries. Thank you, Lou.
Okay, you can hear me?
Yes, loud and
And you can see me, and you can see that. Oops, what happened there? Just a moment. Just a moment. Just a moment. Start that again. Let's use it this way. The title of this talk is Pythagorean Mysteries.
Woo.
And it shares the theme of what was the previous title, as you'll see. The way to think of this talk, I believe, is that imagine that we're sitting at a table and drawing some things on a piece of paper, all right? So I want to talk about the Dirac equation for a little while, and you'll see where this goes as we take it. You'll recall that in special relativity, E squared equals P squared plus M squared, where E is the energy, P is the momentum, and M is the rest mass. Here I'm taking Planck's constant equal to 1 and h bar equal to 1 and the speed of light equal to 1 by convention to make formulas simpler. And Dirac, this refers to what Dirac desired to do, because he was confronted with the fact that there's this nonlinear equation about the energy, but he wanted to take a square root. And so he tried. Is there a question? You need to mute, right, or ask the question. Dirac wanted to take a square root, and he tried the following stratagem. If E was equal to alpha P plus beta M, or alpha and beta are some associative but not commutative algebra elements, then if you square the E, you see what you get. You get alpha squared P squared plus beta squared M squared plus alpha beta plus beta alpha times PM. P and M are commuting, of course. And so if he wanted to get P squared plus M squared, he could do so by taking alpha squared and beta squared equal to 1 and alpha beta plus beta alpha equal to 0, anti-commuting. And so he decided to use that idea to get a linear form for the energy, or for the energy operator. Now, it's probably a good idea to go back and remind ourselves how that formula comes about, E squared equals P squared plus M squared, because the Pythagorean theorem is in there from the very beginning. There's a key thought experiment in elementary special relativity that I like. I don't know if this thought experiment goes back to Einstein or not, but it's a well-known thought experiment. You have a photon clock, which consists of a little tube with mirrors at the ends, and the photon is bouncing back and forth between the mirrors. The length of the clock is L, and so one tick is L over C. Now, speed of light is not equal to 1. And so that's a unit of, that's one tick, one increment of time for an observer for which the clock is stationary. But now we put the clock on a moving platform, and so to an observer who watches the platform go off to the right at velocity v, the photon appears to go up the hypotenuse of a right triangle, and the right triangle has base d and height L, and so the distance along which the photon travels for the observer on the ground is the square root of d squared plus L squared. We're using the Pythagorean theorem. And then we can work it out. If delta t prime is the time for one tick seen from the ground, then we have that delta t prime multiplied by the speed of light, that's going up along the hypotenuse, is equal to the length of a hypotenuse. And on the other hand, d is equal to v delta t prime, because that's the distance that the clock traveled along the ground from the point of view of the ground observer. And distance equals rate times time, and the rate of travel relative to us is v. So squaring the relation in the first case, delta t prime c, we get c squared delta t prime squared equal p squared plus l squared. And d, remember, is v squared delta t prime, and L is delta t c, and we put that in and solve for delta t prime and find that delta t prime is delta t divided by the well-known factor, the square root of 1 minus v squared over c squared. So that factor, square root of 1 minus v squared over c squared, is an artifact of relativity and the Pythagorean theorem. And then to get the other relationship, you have to go over to a little more thought, which I'm just jumping to, that the non-rest mass is equal to the rest mass divided by that same factor. That's a relativistic mass. And then square that and rewrite it, and it turns into, and I won't walk you through the algebra, e squared is p squared c squared plus m naught squared c to the fourth, where p is mv. And then you let c equal to 1, and you get e squared equals p squared plus m squared, and I don't write m naught anymore. And there you have it. So this is all about the Pythagorean theorem in relation to a little bit of a change in the space having to do with the speed of light being constant. Now going back to Dirac. It's also worthwhile to remember that we can make models for this algebra. The simplest model, one of the simpler models, is to let alpha be equal to minus 1, 0, 0, 1, and beta to be equal to 0, 1, 1, 0, permutation matrix. And then you'll note that alpha times beta is this anti-diagonal matrix whose square is minus 1. And indeed, alpha beta squared is minus 1. We can try going from there to quaternions and other things, but I won't do it here. What did Dirac want to do? He wanted to write a Schrodinger type equation. I d psi dt is equal to the energy operator applied to psi. And he wanted a good energy operator. And he wanted this because he wanted to write an equation that would be correct for special relativity. And then let's recall the motivation for the operators. If you had a plane wave, and I'm writing it in my convenient coordinatizations where the speed of light is equal to 1 and h bar is equal to 1, we can write a plane wave as e to the I px minus et, where p is the momentum and e is the energy values. So then you see that if you multiply, if you apply I d by dt to psi, E comes out. And if you apply minus I d by dx to psi, then P comes out. And so one takes the energy operator to be I d by dt and the momentum operator to be minus I d by dx. And the mass operator is just multiplication by the mass. And so what Dirac wants then is to write the energy operator equal to alpha, the non-commutative thing, and beta, alpha times p hat and beta times m hat, where m hat is m, as I said. And now we're in the domain of the Dirac equation. But now let's go quickly to something nilpotent. So if you took the Dirac equation in this abstract form as energy operator minus alpha p hat minus beta m hat equals 0 as an operator applied to things, then that would solve it. Then you could multiply this equation by beta alpha. And if you did multiply this by beta alpha, then you could use that operator instead of the other operator. Now multiplying by, yes?
So you assume we won't have to get it. You assume
was there a question?
I thought there was from Sean. Today. But he's
No
got,
question?
he's got silent again.
We're muted.
You'll see the consequence of this in a moment. If we use this operator, and then I see it in the order in which I did it, I would rather use the next slide. No, wait, no, I think I lost a slide somewhere in there. That's all right. Just consider what will happen if you apply this operator, any operator, take this operator and ask what will happen when you apply it to the plane wave. There, it's superimposed. What happens when you apply this operator to the plane wave? Well, the E hat will pull down an E, the P hat will pull down a P, and the M hat will pull down an M, right? So when you apply the operator to the plane wave, you will get a corresponding thing. And if I took this operator rather than that operator, then this is what I would pull down. I would get that the operator, this operator, applied to psi is equal to beta alpha E minus beta P plus alpha M applied to psi. And you will note that this squares to 0, which is part of the Pythagorean mystery. So now we're just looking at the algebra. We have that E equal to alpha P plus beta M, then E squared is P squared plus M squared. We cooked it up that way. But if you take U to be equal to beta alpha E minus beta P plus alpha M, then you see what happens when you square it, because beta alpha is the square root of minus 1, and you get minus. And beta squared is 1, and so is minus beta squared, and alpha squared is 1. So you get these three terms, and all the cross terms cancel because things are anti-commuting. So this is 0 because of Pythagoras, or because of Einstein. E squared equals P squared plus M squared. So this is Peter Rollins' point about how a nilpotent operator arises in the contemplation of the Dirac equation. And so if we define, now I've said it in the order I wanted, but I could have said it a little earlier. If I let the operator be beta alpha E hat minus beta P hat plus alpha M hat, then d phi equals 0 is the Dirac equation. It's just the rewrite of the original Dirac equation. And if you wanted to see what it looked like as a differential operator, you put in those things and you have this. There's your Dirac operator in the nilpotent or Rowland's form. And then what we have, if we then look at the plane wave, which I said before, but now it's on the slide. Here's the Dirac operator. Here's the plane wave. I apply it to the plane wave, and out comes U. Because U just replaces all the operator positions by the corresponding eigenvalue, energy E, momentum P, and mass M. But that says that d psi is U psi, and so if you apply d one more time, you get U squared psi, which is 0, because U squared is 0. So U psi is a solution to the Dirac equation. Applying U to psi creates a solution to the Dirac equation. And applying it again annihilates that solution, because U squared is 0. So you can think of U as the annihilation operator for the fermion U psi. And that's the Dirac equation from this point of view in a nutshell. Now I want to follow this out and show you some things. One thing that's worth understanding is what happens if you were to then rewrite for a particle traveling backwards in time. Change the sign of time. I just go through this quickly. If you change the sign of time, you change the sign on the E, and then you have a new U with a minus sign where there was a plus sign before. And then you find that U plus U dagger over 2 because of niceties is this, and U dagger plus U dagger U over 4, you can just check it out, is equal to E squared. So in other words, skipping the algebra, we have that U squared is 0, u dagger squared is 0, and u dagger plus u dagger u is a scalar. We can normalize this to 1 if we want to. That's fermion algebra. And so you see that fermion algebra arises naturally in this way. It's Peter's point. So now I want to talk about trying to solve the Dirac equation for certain things. And I'm going to be using a paper that we wrote, which if you want to see this paper, it's in the Foria. And I'm staying with the 1 plus 1 Dirac equation. And now the notation changed a little bit here because I decided to display the paper. But otherwise, things are not much different. Here's what I called alpha, and here's what I called beta, and here's the square root of minus 1. But now I've written a Dirac operator of a particular kind here, and you can just bear with this, because I have to tell you what we were trying to do. We can write solutions to the Dirac equation. So why not write solutions to some Dirac equations that maybe hadn't been thought about this way before? There's more than one Dirac equation you can write, more than one operator you can write, depending on how you choose the algebra. It has to satisfy, of course, the energy squared equals p squared plus m squared condition, but you can do it with different algebra. You can adjust the algebra. And Majorana, back a long time ago, had the beautiful idea that maybe you could rewrite the algebra so that there were no square roots of minus 1, so that the solutions would be real. And if the solutions were real, then Majorana felt he would be describing particles that were equal to their own antiparticles. So it is of interest to consider solutions to the Dirac equation where the algebra has been, the matrices have been set up so that the differential equation is actually entirely real. And this is such an example, where you'll notice that in my original Dirac equation, let's go back to it, there were some i's. There are always some i's to begin with. Where's that operator? There it is. You see, there are these natural operators that come from the fact that the energy operator is I d by dt, and so minus I dt, or minus I d by dx for momentum. So if you work the algebra right, you can get the i's to disappear and write a version of the Dirac equation like this one, which is a 1 plus 1, one dimension of space, one dimension of time, real Dirac equation, or a Majorana Dirac operator. All right? So if you take that one, and notice there's an epsilon eta there whose square is minus 1. So there is a kind of surreptitious square root of minus 1 happening here. Now, the idea was to take the Majorana equation and then solve it over the complex numbers by making it into a nilpotent operator and then applying our method, right? The one we just described to you to find solutions by multiplying by the correct operator. So how do you do that here? Well, one way to do that here is to multiply by, and I just ask you to bear with me, if I multiply by I eta, remember eta squared is 1, then we have, now I'm using I, but I'm going to use it just to get solutions over the complex numbers and then take their real parts, okay? The usual idea. So I'm multiplying this by I eta, and then I have I eta here, and then I have I eta epsilon here, and then I have I epsilon, with a minus sign, the eta disappeared. And we have this guy, and this guy is the nilpotent operator. This one will do the same job as what we had before. And if we then let psi be equal to the plane wave for testing and apply it, then you will find that you will get d psi is equal to, and here's the nilpotent, it's in the form of A, which is something times E and P, and IB, where that's minus epsilon m. You don't need to, look, I just want to tell you the story and show you the result. So we go ahead with that, and we note, however, that the A that I have described here is equal to E squared, because that's 1. Eta squared is 1, and epsilon eta squared is minus 1, so I get E squared minus B squared, and that's M squared, and the B squared is equal to M squared, okay? And then you can see that A plus IB is nilpotent from that. So we've broken apart the E and the P and the M in a certain way. And then we can then take A plus IB and multiply it by the psi. And psi is e to the I theta, where I've written theta rather than px minus et. All right? And we get A cosine minus B sine and B cosine plus A sine. And then you can take the real or the complex parts of that, and they will be solutions to the Majorana equation. You go ahead and do that, and you get a matrix, and the columns of that matrix are the solutions. And then you change to like cone coordinates. You let R be equal to 1/2 of t plus x, and L, that's going to the right in the Minkowski plane, and L to be 1/2 of t minus x. And you can rewrite the px minus et in like cone coordinates, and then you have an e minus p and an e plus p and an r and an l. And so in the end, after you do all that, you get a pair of equations instead of a single equation. You get this equation. You get that d psi 1 with respect to left is a multiple of psi 2. And d psi 2 with respect to right is a multiple of psi 1. And these are satisfied by these sine and cosine formulas. So we get a solution to the 1 plus 1 Dirac equation in terms of trigonometry in this way. So you could just stop here and not worry about how we got to it, but I thought it was interesting to tell you how we got to it. That if you rewrite the Dirac equation in like cone coordinates, it has this very simple left-right exchange of two functions character. And you'll notice that in this case, there's no I here. This is the Majorana case where it's a real equation. And it has real solutions in this form, where there are trigonometric sines and cosines in this fashion. And of course, you can do the exercise and verify that you're looking at a solution to the Dirac equation just from this. Just go ahead and do it. A little bit of exercise of half a page of algebra, where e squared equals p squared plus m squared, of course. So it's interesting to see these direct solutions emerge. The solutions are fundamental in that they're distinct. They seem to be distinct from the usual solutions that emerge from the Feynman checkerboard model. And it's in the above equations that form the basis for the checkerboard model that's obtained by examining paths. Now that's the point that I want to talk about a little further. In Feynman's model, you think about paths on a checkerboard. I don't know yet how to interpret these solutions, which are trigonometric and very simple, in terms of paths on the checkerboard. Let's look. The basic pattern of what we just talked about is this. Let's look at it. I could take e to the I AR plus BL, and I could let psi 1 be equal to A psi, and psi 2 be equal to M psi, where AB is M squared, A is E minus P, B is E plus P, right? And E squared minus P squared equals M squared. And then I calculate d psi 1 dl brings down an IB, and we get IAB, and I get IM psi 2. Now we're over the complex numbers, of course, so there is an I. And d psi 2 dr is equal to IM A psi, which is IM psi 1. So this is the basic form of things, like that. And this is then giving us solutions in the usual case where there's an I. But it's just coming from this very simple trigonometric formula, like that. Now what? And you could forget how we got there just to think about these are going to be giving us Dirac solutions. Here's the Feynman checkerboard, Minkowski space, and you can go to the right or you can go to the left at the speed of light, which is equal to 1. And you can consider paths that start you here and end you up over here by zigzagging on the board, either going to the right or going to the left, and going on and on like that. And Feynman, in his book with Hibbs, wrote down an exercise. He said, define an amplitude by the sum over all the paths that go from your initial point to your final point, all combinatorial paths, I to the number of corners in the path. Every time you change direction, you take an I. You could also take -1, and then you would be doing the Majorana one. And he said, and this will solve the Dirac equation. Prove it. It gave rise to a large number of papers. I think people are still writing papers about this. Why is this related to the Dirac equation? Well, you can see that very easily by the following thoughts. I have a point in discrete Minkowski space, so this is the left-right coordinate. And I'm going along, and here I continued going along to the right, and I add 1 to the right-hand coordinate. Here I went to the left, and then I went to the right. So I can write what Feynman's propagator does. If I were to end up at b+1, but be coming from the left, then I would have the left path, whatever it was, the left path coming in, and then I went to the right and I cornered, so I have to multiply by I, and so I multiply by I the paths that come in that way, and I get a formula that says that psi left is going to be at a new point is equal to the psi left at the old point plus I times the psi right, the ones that take a corner. The set of paths coming in here are the ones that come from the right and that come from the left. And when they come from the right and you're measuring left, you multiply by I. So now, if you take the difference, you see that this says psi left at AB plus 1 minus psi left at AB equals I psi right at AB. And that difference is a partial derivative in the discrete world at the right-hand coordinate. So d psi left, d right should be I psi right. And similarly, d psi right, d left should be I psi left. So that's the simplest solution to Feynman's exercise. That if you look at this as a discrete process, then the differential equation for the discrete process is exactly the Dirac equation. So there's no mystery there. And we can define solutions. But how do the path solutions correspond to actual continuum solutions? How does the checkerboard solutions look in the limit? Well, there's a nice story, and this is what Noyes and I did a long time ago. There's a nice story, at least one of many stories for understanding the limit. The idea is as follows. If you use discrete differentiation, then the correct thing, rather than x to the n, is this interesting beast. X upper n is x times x minus delta times x minus 2 delta, all the way down differences a ways for n factors. And then if you take the discrete derivative, where delta is the step in the discrete derivative, you find that the discrete derivative of x upper n is n x upper n minus 1. So you can mimic calculus there. Not hard to see it. But this looks like part of a choice coefficient, doesn't it? If you were to divide this by a factorial, why then you would be looking at a choice coefficient. So what you want to do is look at x upper n divided by delta to the n times n factorial, and then it looks like a choice coefficient of x over delta n. Why am I interested in that? Here's a choice coefficient, you see? So I can say that the x upper n over n factorial is an appropriate evaluation of a choice coefficient. The reason why is because a path is a kind of choice. And if you were on the checkerboard, then making a path up through the checkerboard is the same as choosing a set of points down along one side. Better to do it with the other checkerboard. Choosing a set of points down along one side of the path, project down here, and you chose this point, this point, this point, this point, and project this way, and you chose this point, this point, this point, and that point. So if I make a choice of points along one side and a choice of points along the other, then that's the path. And so I can take the expression, the choice expression for one, times the other, and then I will be enumerating the paths on the Minkowski checkerboard. And so that means that when I write somebody like this, product of choice coefficients, I'm actually enumerating paths of a certain length on the checkerboard. And so then you can write down the paths in terms of the choice coefficients. And then you can take the limit as delta goes to 0, and the choice coefficients turn into x to the n over n factorial expressions. And so this is how it looks. You start with choice coefficients and you take the limit and you end up with series, like exponential series of powers of r and powers of l divided by the factorials. And then you put them together and you get the solution to the Dirac equation in the continuum limit. And each one of these expressions here is, you look through it and you see all those combinatorial paths because it's a limit of those product of choice coefficients. And so we can go to the limit and see what kind of series we get. But these, in fact, these series that I'm writing down here satisfy the Dirac equation, but they are not exactly the same as what we were doing with the trigonometry. They feel like they're related to it, but what we did in this very elementary trigonometry that I showed you before seems to be a little different. And so the question is there a lattice sum interpretation for this solution to the Dirac equation? Well, that's part of the Pythagorean mystery, but very technical. Let's pull back now and return to Pythagoras. Maybe you would like to see a proof of the Pythagorean theorem. Here's a favorite proof. You drop a perpendicular, and we have divided the hypotenuse into x and y. And then there are similar triangles. The left triangle is similar to the right triangle is similar to the larger triangle. So I can say that x is to a as a is to c, and that y is to b as b is to c. Those two similarities rewritten become xc equals a squared and yc equals b squared, and you see what they say. xc, if you put a square on this hypotenuse, then xc is the area of the left rectangle of the divided into which the square is divided, and yc is the area of the right triangle into which the square is divided. And this says that the left rectangle is equal to the area on that leg, and the right rectangle is equal to the area on the other leg, and the sum of them is equal to the area of the hypotenuse, and so we have a squared plus b squared equals c squared. That's the classical Pythagorean theorem. Then over on the other side, we had alpha squared and beta squared are 1, and alpha beta plus beta alpha equals 0, and we have the nilpotent alpha beta c plus alpha a plus beta b. I rewrote it more in a prettier way for the sake of the math. And you square it and you get 0 because c squared comes in minus, that's a square root of minus 1, and a squared plus b squared, and all the other terms cancel by anti-commutativity. So how are these related? I don't know the answer, really. It feels like we walked into another dimension of the Pythagorean theorem that, of course, the Pythagoreans were not aware of, or maybe they were in some other way. What are we missing? I don't know. Let me leave that slide. But the closest I can come to this kind of question is the work of at the moment, is to the work of John Wallis in around 1675. Wallis found a geometric interpretation for the square root of -1. It was ignored. Probably it wasn't expressed as succinctly as what I'm showing you on this slide either. But Wallis was one of the pioneers for expressing the real line as both negative numbers and positive numbers. And Wallis was aware of the similarity relationships that I just showed you about the Pythagorean theorem. And he was taken by this similarity relationship. H is to x as y is to h. These two right triangles fit that way, and you get that h squared is equal to xy. The length squared of the perpendicular is equal to the product of the two parts into which the hypotenuse is divided. And Wallis said, let's sit this triangle upon the real line so that the x is -1 and the y is +1. And then we would have h squared is -1, and so h is the square root of -1, and so we shall interpret the square root of -1 as a unit length in direction perpendicular to the real line. Back in 1675. This is often attributed to Gauss and Argand around 1800. But it is definitely the case that Wallis said this, but perhaps didn't superimpose it on Cartesian coordinates, which didn't quite exist yet. But here's our modern picture, which is exactly that, of course, for the complex plane. And here we are superimposing strange numbers with ordinary geometry. And that seems to be what this question is about. Is there not some superposition of these strange numbers with the ordinary geometry that we're talking about here in the nilpotency? But I haven't gotten it to fit together yet. I just do little exercises like this. Like you could try superimposing Wallis and Clifford, and then you would have alpha and beta instead of -1 and 1, and you would have an h up there, and h is alpha beta, which is the square root of -1. So we can produce the square root of -1 in a space where perpendicular to the square root of -1 are Clifford elements like that. You can play around with this if you're interested. But then there are other things that happened in the course of the discoveries of algebra. So for example, Grossman had the idea of introducing non-commutativity. Wedge product of v and w is minus the wedge product of w and v, in order to have an algebra of vectors so that the wedge product of two vectors would represent the area spanned by v and w. Then you see that an individual vector should square to 0. And if an individual vector should square to 0, then a linear combination of them will square to 0, and that will force v wedge w plus w wedge v to be equal to 0. So the anti-commutativity is forced for very similar reasons to the ones where we showed how to invent Clifford algebra a la Dirac. Here we're inventing Grossman algebra because we want 0. And Grossman algebra and Clifford algebra are closely related to one another. So there is something going on here in the theme of labeling the space with the non-commutative algebra. And I want to remind you, I'm just asking questions and we'll stop soon. I want to remind you how that comes about in relation to electromagnetism itself and gauge theory. Remember that in the 1920s, Hermann Weyl had the insight that electromagnetism came from the properties of a line element in space-time. And he wrote something like this: a line element in space-time, coefficients dx, dy, dz, and dt, and then noted that if you looked at this as a Grossman form, dx squared is 0, dy squared is 0, dz squared is 0, dt squared is 0, dx dy is minus dy dx, right? A Grossman form. And you differentiate it, and you look at what you get, and respect the fact that we're dealing with differential forms so that dx is 0 and so on, and dx dy is minus dy dx, that change in the underlying geometry of the space, labeling the space with these imaginary quantities, why then you get the electromagnetic field. So that he saw that the line element contains the formalism of the electromagnetic field. And he then suggested that taking a trip around a curve in space-time and looking at how the result changes should measure the electromagnetic field, and so the electromagnetic field should be unified with space-time. It didn't quite unify very well with general relativity. He was doing this around 1920. But the formalism is perfect and really does produce electromagnetism in relation to differential forms. And later, people understood that this really was happening, but it was happening at the quantum level. That is, later, people understood that if you looked at the holonomy of exactly the kind of thing that Hermann Weyl was interested in, his gauge, and put it in a quantum context, then you could find interference patterns where there shouldn't be any because there's no electromagnetic field to change the particles, but there is a potential, and the potential is what's involved in that line element. And so these things reach into the structure of the really deeply into the structure of the physics. And it's still a mystery why it is that this is working as well as it does, or what is really the relationship between electromagnetism and quantum theory that is making this work. The formalism, of course, is well worked out. So this talk ends in a confusion of questions about how non-commutative algebra and the Pythagorean theorem conspire to yield fundamental physics. Thank you.
Okay. Right, so we have Dennis hand up straight away, arm up in fact, so let's go with that.
I'm sorry you missed it, Lou. We answered all these questions over the last 2 days. What you're working with when you put your alphas and your betas into the Dirac equation, you're working with an algebra called the split quaternions. The split quaternions have two...
Yes, that's correct. I'm working with the split quaternions at the, and I didn't go over to add square roots of -1 to make them into the quaternions from this point of view.
Yeah. These come out of the dihedral, the four-dimensional representations of the order 8 dihedral group. Those four-dimensional representations in superposition form our four-dimensional space-time. We did that on Monday. They also derive gravity and classical electromagnetism from them, using them as gauge potentials. So what you really want is you want to use 4x4 matrices for your alphas and your betas.
You're pointing out that I stayed in 1 + 1. Of course, all this is written out in 4 dimensions.
But there's your connection between the Pythagorean distance function and the split quaternions.
So was there a question?
No, I'm just saying that you should have been using split quaternions. So you know about them anyway.
Yeah.
But that's the answer to your question.
Yeah, sure.
Okie dokie. So, John, you want to say something? Ask something? Then you need to unmute yourself.
Yeah, hello, there we are. Yeah, hello, lovely as usual, great fun. I think the other connection, well, you've got the relativistic connection in there as well. I think the other connection here is the quantum connection to relativity as well, which of course you touched on, and I think that's an interesting factor So have you considered the way that the quantization, you see, you're putting quantization at the moment in terms of a wave function, and having a look at the way the wave function comes out and runs through the Dirac equation in that. Have you considered going one step backwards from that, and looking at the thing in terms of just the relativistic, just in terms of the relativity and running through the whole thing from the relativity, rather than putting in the quantum mechanics at the point at which you're doing it?
Well, I'm not sure what you mean by taking one step backward. You can go. What do you mean if you say just look at the relativity?
Well, having a look at the vibrations of relativistic vibration in the way that de Broglie was doing that, having a look at the nature of the transformations of time. I know you've done this in other contexts as well, in terms of the transformations of time and in terms of the transformations of frequency. And at that point, rather than starting from a point where you already have a wave function involved, and you just be like kx minus omega t.
Well, I'm not sure what structure you have in mind of Ubuntu. So we could be, for example, at the level of de Broglie's thesis.
At the harmony of
there was no wave function yet.
There was no wave
but he's being very careful about the relativity.
Exactly, about the harmony that goes in there. Can we take it back to that level? Have you considered that as the question?
I considered it at the level of talking to myself along the lines of, over there on the desk is a copy of de Broglie's thesis. Why don't I pick it up and actually walk through it, thinking along this way? Yeah, but I haven't done it.
Is it Kauffman's translation or is it the original?
It's a translation.
The translation. That's very good, that translation, but...
You recommend the original?
If you can read it, yes. I talked to Kauffman about this. There's a slight misinterpretation in terms of the way that, if you read the original and look at the English translation as well, we did discuss at some stage putting out a revised version of the translation because there's some subtleties missing in the translation that might be amusing. If you get hold of the original one as well, it's fun to look at those too, if you read French.
No, I'll do that. Mm-hmm. Someone should put out a facing translation.
Yes, you're right. That would be a great way to learn French, because de Broglie's French was so beautiful. It's some of the most beautiful French I've ever read. It's poetic in prose. It's beautiful. Like I said, it would be an honour to learn it from de Broglie, of course. What a lovely thing. Good idea. We should do that.
Another project.
Could I possibly suggest we just have a quick look at a few pictures? This is something, Lou, thanks for. This is just sort of following up on John's comment of supposing we dispense with quantum mechanics for a minute and just go back to Minkowski space and ask the question, well, can we see this? And the answer is actually yes. Can I just share a couple of pictures? Can we do that? And I just think you may be excited when you see it, that's all.
Yeah, sure. Are you saying you wanted to show something?
Yeah.
Just a couple of pictures.
Yes, of course. Go ahead.
Yeah.
Because I think you'll see. Let me just find it. Okay, so just have a quick look at this. So take all of the stochastics out of what you're doing. Right, just look at so imagine just putting points on the world line and then saying, look at the forward cones, which are in blue, look at the backwards cones, which are in red, take the intercept, and you have this rather stylized.
So you have paths moving forward and backward in time in your picture.
Well, actually, the thing think about is just think about the areas. Those are the time-like areas between the events. So forget about the past for the time being. Just think about those areas.
All right.
If you color them a little bit a la John with photons, right, and so that you have continuous paths that go through the events, you see that you have these funny oriented areas. And if we then just go on and ask, well, what happens with the boost? Well, when you boost, the actual areas, the physical area, the Euclidean areas of the causal areas just look like this. And so if you go to your LR coordinates, what happens is the entire chain of areas is stretched in one way and shrunk in the other way in such a way that the area is the same. Mm-hmm. So looking at the whole thing in the line-time coordinates is a much better way of doing it, because in the end, those two, the left and the right, are independent, whereas space and time aren't. So let me just fast forward this bit and say, okay, here's this on the top left. Those are the paths that we looked at and said that, okay, there's these causal areas. And I colored them in 4 colors because really, if you think of them in terms of lines or paths, there really are 4 kinds. Now, let's get rid of the left half, and you'll see, oh, this looks like a Feynman path, and we've just boosted it. Now, notice what happens when you boost it. What happens is that the earlier events get mapped onto the x-axis. So as you pull this thing as you look at it from a higher speed, notice what happens. So that the events get farther and farther apart, and you end up making a pattern on the x-axis. Here's what it looks like. So lower left, our x-axis out here. Notice how in the middle it's blue, because you're very near the most recent event. As you go out in time, as you go out in space, away from the time axis, you're looking farther and farther back in time. Okay, these areas, these little areas, you bring them close to the x-axis as the velocity increases. So if you just map that, there's the map of color. Right? So we're just saying, look along this axis. Oh, well, it's blue in here, and we're going to say, blue is 1, red is -1. We see this funny pattern. Okay? I call that a history map because it really is a mapping of the time sequence of this thing in space. And this is not many paths, this is a single path. You're taking a single path, and you're going, look at it from different velocities. So does that, there's no quantum mechanics here, right? This is just saying we have events that are in space, we're going to look at what happens when you look in constant space. So let's just look at that pattern, because the bottom right pattern may look a bit familiar. Any of you have looked at Feynman and Gibbs, that's the propagator for the electron non-relativistic, because you're near the t-axis. So if we just compare to the actual, for some reason it's not. One to go in the next one. Okay, there is the actual this funny square thing that we looked at, which is just Minkowski space. That's all it is, with a discrete, deterministic periodic signal. The square thing is just Minkowski space. The smooth thing is the Feynman propagator, and they're synchronized by a single number, and that's the mass in terms of h bar. Okay. Right. So Minkowski space knows all about this. Right? Minkowski space knows all about the you know, the Clifford algebra to find this thing. And that smoothing that you question is actually a filtering process. Because when you take a Fourier transform, there's this funny thing that John talked about, that when you're looking at things differently from frequency space and configuration space, in actual fact, when you bring in the Fourier transform, it's a miracle and in sense, because you do get this very, very simple picture of what's going on. And so, one way of thinking, how does this thing smooth out when you bring in quantum mechanics, which is really just a smoothing operation in Minkowski space? Well, what actually happens is, if you think of this squared off propagator as being like a square wave, what actually happens in the filtering process in the Fourier domain is it throws away everything but the longest wavelength, right? Because those corners require high frequencies to build. So in Fourier transform, when you take all this stuff to the transform domain of space, and it comes out this beautifully simple thing where you just find the 3 quantums. That is the reason for that is simply that when you do that, you're smoothing this thing out by throwing away the high frequency stuff and just pulling in the low frequency stuff, and you get this harmonious feature.
I'm really pleased you brought that in, Garnet. I think that's absolutely beautiful in conjunction with what Lou was just talking about. And I think the combination there looks to me like a fantastic potential piece of work.
Well,
yeah, I'd like to look at that more carefully. If you would send your slideshow over to me, and also the paper, if there's one that corresponds to this, probably more than one.
Okay. Actually, the slideshow, it has to be particular tonight, but I'll send you a paper that has it in. So,
yeah, the talk Garnet was referring to, I gave one this morning because somebody fell out, so there are slides for that one as well. I'll send them to you as well.
Great, please do. I put my email address in the chat line in case you forgot.
Thank you, that's lovely.
Okay.
No.
So what you're saying, Garnet, is that by kind of taking the Feynman paths but looking at them as a guide to the way the particle could move, you can think of it as a classical particle kind of guided by the Feynman path structure?
Well, that's right. But I have to say, I try to get people away from the Feynman path. It's a beautiful idea, but when you get to the relativistic case, notice that every Feynman path you've ever drawn, it has a complement, and you can draw it in terms of the areas. And then when you look at the areas, you realize, oh yes, well, special relativity really is about areas. Right? You can go to four-dimensional space-time, but the things that are of interest are always the space-time planes. And because, in actual fact, the space-time planes, if you define them correctly, there's one space-time plane in which you will have time dilation and length contraction, and in the rejected space, there's nothing happens. Right, so it's just, there's no chance for phase to come in. But in that one space-time plane, the phase comes in, right? Because you have time dilation. So that's why you always get these funny 2D aspects to the Dirac equation.
Hey,
right?
guys,
and it's why in the end.
And the question I'm asking maybe is better shifted into a context like yours. I'm saying, here's a beautiful solution to the Dirac equation, but it ain't obvious that it's a sum over combinatorial paths, and maybe it just isn't. It should be thought of in a different way.
That's right.
Guys, sorry, I have to break. Shut up! I mean, you are very noted.
John Torde is waiting.
Already
like it's beautiful stuff. And you know, like I'm interested, I'm sure lots of people are interested, and maybe it could be a separate thing. But I mean, we were already running late, and you know, because of difficulties here. So I really think we need to go over to John Torde now. Although I will say,
Sure.
yeah, I mean,
Thank you.
I just wanted to say something, a few things, but I won't. I'm just the relationship with naught zero and the point is actually a very big issue philosophically, and so this goes back to the whole kind of Pythagorean thing, and also area itself. But anyway, we can converse, Lou, about that. And I think now.
Excuse me, I want to make a just slight announcement.
What do you want?
Does everybody know that we're carrying on full tomorrow, and Thursday is going to be our day off? Okay?
Got it.
Yeah, people have just come in, Mark and John. That's what we're doing. It's a full day tomorrow, and Thursday is the day off. Okay?
Thank you. Yeah.
They need to know that.
Yeah. No, I think because Barbara is sending out that it's like a rearrangement for tomorrow. It's because we're being shut down here. We can't come in here tomorrow, so that's why we're doing the day out tomorrow. So yeah, is that right? Have I got it right? Yeah, that's it. So that's right, isn't it? Yes. Yeah. No, we're doing the day out on Thursday. Sorry, I've got
day out on Thursday.
The day out is now on Thursday. We're shut down on Thursday because there's no water in this building, so they're shutting us out on Thursday. So we brought Wednesday forward, but it had to be rearranged in terms of who's available when. But Barbara is emailing that on ANPA chat to everybody, so you'll see what's happening tomorrow in terms of who's speaking when. And then Thursday will be our free day, and then Friday is changed slightly, but not very much. Anyway, so can we, does anybody, let's have a look, so Barbara's, yeah, I think we need to just start now, actually. I don't know where Barbara's gone, because we usually have a short break in between, but we're running.
We can go, just go.
Yeah, I think so. So, okay, so John Torde, I haven't even got my piece of paper. You give us your title, give us